Hi there, and welcome to our latest tutorial in using Bridge Designer 2016, or as I like to call it, West Point Bridge Designer, the 2016 version, second edition, um, for BCIT's Technology Teacher Education 4044 class. And this is taking a look at a project that I've used with my high school students for many years, and from time to time with my BCIT students. I think it's one of the best combinations of gamification and with real engineering background behind it, so that it turns it into a good educational tool in that it's fun, engaging, challenging, and also realistic in the things that you can learn. So before we get into that, I'd like to point out that I did leave some ambiguity in which files to download. And I wanted you to get the Bridge Designer 2016 edition. And I know on the Bridge Designer site that it doesn't take you directly to this download page. So it's https bridgedesigner.org/download, and it should look like this, and then you can download the software either for your Windows or your Macintosh computer. Okay, and while we're talking about some of the resources that are available on the site right here, um, Colonel Stephen Ressler, who initiated this, and the people who've worked with him on it since, have come up with some neat features. And one of them is a thing that we're using, which is the local contest feature. And this is a link that you probably want to save for when you're working with your future classes, because I've assigned you guys a local contest code, which sets up all the site conditions. And I'll talk about that and a little bit about why I chose the site conditions that I did for you in a minute. But you can set up site conditions for your students so they have to build using one specific site condition. And why that's important is because West Point Bridge Designer software has been around for a long time, and there's many tutorials out there that show you how to solve a generic bridge pretty much as cheaply as possible. So there's a high likelihood that if you just say to your students, go out and build the cheapest bridge that you can, being the bright young people that we know them to be, they'll do a little bit of research, and which is good. Yeah, we like to encourage research. We don't want people going out and saying, "Oh, I'm going to solve it my own way because I'm the best person on the planet at this." We want people to go out and do research. But unfortunately, what they'll find is that the optimal general case solution for this bridge is probably already published. And so if you set up a local contest code with specific site conditions, the chances of those conditions already being published is slimmer. So you can make it a more fun competition. It also removes some of the variables from the design and ensures that everybody's working on the same page and makes the competition a little more competitive. So anyway, this document right here, you can download, and that talks about how to set up your local contest code. And again, if you're one of my students right now, I strongly recommend downloading and saving these links somewhere, because you never know when you're going to need them. So there's the local bridge contest. The other thing that's worth noting as you go around the Engineering Encounters website is that Colonel Ressler has also developed a really neat file folder bridge challenge. And while for the shop class, I tend to like to use wood and materials like that and get the students onto tools right away, because that's part of the reason why you're teaching in a shop class. And some of the engineering that we do in the class is as a way of bringing students who are interested in engineering and technology and getting them working with their hands and making real things. This is a great project if, for instance, your shop is shut down for a while, and like the first few weeks of my practicum, the wood shop was all shut down because they were upgrading the ventilation system and we couldn't have any dust extraction. Other schools have gone through seismic upgrades, and the principals come into the shop teacher in September and said, right, we hope to get you back in your shop by March, but for the next 6 months, you're in a portable. It happens. Yeah. you want your shop seismically upgraded, um, they're not going to be able to do it while you're in there teaching every day. So sometimes having a couple lessons like this tucked away in the back pocket. If you're going off on leave for a while, you've got to have a small operation done or something like that. You're going to be off your feet for a few weeks. Maybe you're going to get a TOC who's not certified in the use of machine shop power tools. Great project for technology 9-10 students to do a file folder bridge, and nothing too much more dangerous than an X-Acto knife and some glue. Although, truth be told, I've sent more students to hospital with X-Acto knife injuries than I have with table saw injuries over the years, but probably just as well. Uh, it's a very, very small number, okay? But yeah, people don't respect the X-Acto knife nearly as much as they should. And then, okay, one of those students, he got injured after he didn't use a backing board underneath, and he cut into the desk. And after I removed his limbs, he had to go get them stitched back on. College of Teachers was a little more relaxed back then. Don't do that now. Anyway, so we're here in Bridge Designer 2016. Take a look at the top corner of your page right here and make sure that it does say 2016. There have been slight changes in the pricing structure for the bridges each year. And you'll notice that the bridge I'm designing is different from the one that I've assigned to you. So my local contest code that I entered for this one is a 06A, where I've given you guys a 05 B calculation. So different contest code, which gives me different site preparation. Now, if you go into the software and start out at the very beginning and just are solving for a generic bridge, this is one of the neat things about the software, is that Colonel Wrestlers built this up so that you actually have to start thinking about like a real engineer. And when you're trying to span a gap right across here, there's many ways to go about doing it. And one of the ways is to bring in earth moving equipment and cut away a lot of the overburden here and get down to the bedrock or as deep as you can go. Maybe you even have to blast to build channels coming down here so you can get down there. And what that allows you to do is it allows you to greatly reduce the span of the bridge, simplifying the bridge, and making for a cheaper bridge. And sometimes, although it's very expensive to come in and move all of this rock, it's actually less expensive to move the rock and build a smaller bridge than it is to build the much longer bridge up here. Because as you start to get into larger and larger bridge structures, of course, the bridge gets heavier and heavier, so you need a stronger and stronger structure to support the weight of the bridge. So anyway, I've given you a specific set of conditions, and it's slightly different. You can see here I've only got a so 1, 2, 3, 4, 5, 6, 7 nodes. So I've got a 4, 8, 12, 16, 20. I've got 24-meter span bridge. I've got one more node in there for you guys. I think you're doing a 28-meter span bridge under your site conditions. So this is maybe not going to be the optimal solution for what I've assigned to you, but it will give you some tips on how this comes together and why I think this is, of all the bridge software out there, the best combination of gamification and actual engineering science that I've seen. And I've been looking for packages that do this in all sorts of different fields for the 20 years that I've been, well, more than that now, that I've been teaching. So anyways, let's get on with this a little bit. We've got our site set up and you started here. Now you may have chosen a bridge template. You don't have to choose a bridge template when you start out, but you can see here, grade in the background, I have a truss template put in right here. It's not a bad starting point if you do. Now you can get through trusses where the vehicles need to move through the truss, and you can also get trusses that come down here underneath and support the load from below. In my experience with West Point Bridge Designer, for reasons I'll get into lately, I've found the through trusses to be the less expensive option in here. Now, I guess before I get that, I kind of skipped over a few things about the site preparation in here. I was going to say also going down lower is a good site preparation. Why don't they do that for every bridge? Well, obviously, you're going to run into environmental considerations. Removing all this dirt right in here is probably not keeping nature nice and pristine. So it may be better to run right across the top. The other thing is if you think about the slopes required to come down in here, uh, maximum gradients that we like to have on slopes for vehicles of somewhere around 6 to 8%. Trains can only get by with 2 or 3% gradients. So if you build it down low and every vehicle that needs to come down here has to roll down this hill and then climb back out the other side, there's going to be some long-term costs and fuel emissions as heavy trucks climb back out that hill every time. Um, if you think about it as a cyclist, it's great to roll down that hill, but you never roll all the way back up the hill on the other side. So there are long-term costs to building the less expensive bridge. So anyway, you can read it. He's got a really nice help section that comes along with this. And let me just find the help section right here. And he's got tips on how to design a bridge if you just go into the help section right on here, and talks a lot about this in here, and you'll find out purposes and how it works, and what's realistic about it, what's not particularly realistic about it. Um, and then he goes into some of the design specifications right in here, and he talks about how some of this all comes together. So if you're looking for good resources, the West Point Bridge Designer help file all on its own is one of the best documents that you're going to find for helping your students figure out how to design and build these bridges. So very, very strong, very useful help file in here. Okay, I think that has a setup where I want to get to for setting this bridge up for you now. Okay, so here we go. We've got a truss template on here, and you can come along and you can add some nodes. Now, we're going to be talking about nodes quite a bit. The nodes for the deck of the bridge are already installed in there. And nodes are really important when we're talking about trusses because the defining aspect of a truss is that it's held together by pinned joints. And what that means is that at a pinned joint, you basically think of it is that you've just stuck two pieces together, you've put a pin through the middle of them. That pencil's not really showing up there right there, but pretend that pencil is a pin, and my arms are the two members that are being joined together, and they're free to pivot about each other. In reality, it's not perfectly a pinned joint, but the thing is, because these members are long and flexible, okay, they're that long relative to the load that they actually will flex. If you don't brace them and support them properly, then they're going to flex just as if that was a pinned node. If you do your calculations based on assuming that you've got a pinned node, it simplifies the calculations greatly, and your actual bridge is going to be a little bit stronger than your simplified calculations would predict. So when we're doing our truss analysis in class, we're going to use these nodes to connect members. And it's important for you to think about the fact that those nodes are free to rotate about each other when we do our analysis. Now, that also explains why you see so many triangles when you put your bridge together. Okay, so right here, by creating a triangle in your truss, what you've done right now is you've pinned these three nodes together in such a way that they can't pivot, because in order for this to pivot about here, it would need to change the length of this member right here. So this member is locking this member in place so it doesn't rotate about that node. Okay, so that really matters. If you come along and try to design something like this with a square or a rectangle in here, chances are that's not going to work for you because these two nodes right here can pivot and become a parallelogram with these two nodes over here. There's nothing keeping this member from rotating about this node. That's why you need to put a cross brace right across here. And now that you've cross braced that, now you've got two triangles and it's braced together so it can't pivot in there. So it's important to think triangles when you're talking about trusses. And in fact, the triangle is one of nature's strongest, I like to call it engineering shapes. In terms of natural shapes, circles tend to be quite strong, but in engineering, it's more challenging to make circles sometimes. Certainly when you're working with multiple pieces of straight material, triangles are a lot easier to build. And so right now, I'm just going to go through and I'm putting all my members in here and I'm making them all the same. Okay, there we go. And as I put the members in, you can see that each member shows up over here. And if you click on this little number button right up at the top, show or hide member numbers, then each member gets a number on it. And you can see this number one, the first one I put in there, shows up over here as number one. And if I highlight that in my member list, it gets highlighted down here. So you can see what's going on with each member. And if I come back in here and let me grab my highlight tool to select, there we go. I can choose one in here and I see member number 8 shows up over here. And each member has a size and a length and a slenderness ratio, all things that we'll talk about in just a minute as we go putting this together. Okay, so once you've got a structure put together, well, I'm just going to delete one of these members right here, okay? And now we've got the dreaded square or rectangle in right here. And when we go to analyze this, okay, run the load test animation, you're going to get this message pop up saying your structural model is unstable. And in fact, this is really nice. You can see that rectangle flashing at you right there, and it's telling you where to look for your error, okay? Here's other examples where you've got a node that's only connected by 2 members right in here. And, you know, 2 triangles, this one really needs something across the top because right now both triangles will pivot about right here. And here's another one right in here. There'll be some compressive force on the top that will cause that middle node to pop up. And so there's explanations for each of those errors that you might be getting in there. Okay, so if you go to run and a load test, and I don't want to move that node right now, and you get that problem, then you've probably missed putting a triangle in somewhere. Okay, let's go ahead and run the load test animation. As the load test goes across right here, you can see that the compressive members turn red and the tensile members turn blue. And that's one of the things that we're going to be taking a look at as we do our manual analysis of the trusses, is which members are in tension and being pulled and which members are in compression and being pushed together. So when we just pause that truck, let's see, there is, oh, my animation controls are somewhere in here. There is a pause. Okay, something about Windows 10 is not interacting nicely with that little window right there. So that truck's going to come down right here, and when it's in the middle right there, you can see that the top members are in compression. Let's go back, and those results are going to show up right in here. And let's see, show or hide. Okay, so we've got right here, when you upload your file, make sure that you've got this little green up arrow right here, right next to your price. That means that the bridge stood up. It keeps track of which iteration you're on up here. You're at iteration 1 for your bridge. So if you want to go back and check out a previous file or a previous attempt that you've made, you can actually just click back here. And if I go back to that, then you can find that right in there. Okay. There we go. See, we went back to our previous iteration, and now you can come forward to your next iteration. So there's an undo feature built in, which is really nice. Anyways, we've ran our test, actually, because I was clicking around with that. I didn't get my test done. And we come back over here, and now you'll see right in here in our load test results that we've got compression force to strength and tension force to strength. So for each member, when it goes through and it does an analysis, if it's highly compressed, okay, then you're going to see it go dark red. So this member right here is at 0.9 of its maximum strength. So this is kind of cool because it goes through and it saves you a lot of work of going through and calculating, well, what's my maximum strength? What's my load on the member? How close is it to failing? If it's at zero point 0.9, it's pretty close to failing, but you could make it closer. You'll notice over here on our tensile members that they're all really, really low. Like this one right here is basically never loaded in tension. It's almost only loaded in compression. Now, of course, sometimes things will get a little bit of tension or a little bit of compression because as the vehicle moves across the deck, the load of the truck changes the forces because the location of the truck changes. The majority of the weight that you're looking at supporting in a real bridge is actually the weight of the bridge itself. Okay, that's called our dead load. The truck is our live load. And so our live load causes some members to be loaded in both tension and compression, but the dead load of the bridge sets the groundwork and means that most of the time, most of the members are purely either tensile or compressive members. So we can take a look at this and how this all comes together right in here and how we can use that for optimizing our bridge design. So right now I'm at 262,000. Again, my bridge is different from your bridge, so don't compare the prices. Just use some of the techniques I'm looking at, and let's see how far down I can whittle this price, and it'll give you some ideas for how you can whittle down your price. Okay, so right in here, all of the bars are the same. Now, before you go in and start doing too much to calculate that out, click on this little calculator because the calculator shows you the cost of the bridge and where these factors come from. Okay, so you've got your material cost. Okay, and you've got this many kilograms of steel at that much per kilogram, and then you've got the two trusses, one on each side of the bridge. You're always going to have two trusses on a bridge like this. You've got your connection cost. Okay, so we've got 12 joints in there. So each of our nodes are joints in here. You have to purchase and assemble in your construction. Your product cost, each time you order a different size of material, it costs you $1,000. So you can think of that as being a charge from whoever's shipping the steel. You're talking to the steel mill and they're like, oh, they want 20 different parts for that bridge. That's 20 different loadings that we've got to do, 20 different shapes we've got to manufacture. We're going to charge them for each of them. The site cost is largely going to be fixed down here. So you're all playing around in that. Because I've given you a local contest code, you don't get to mess around with that very much. Anyway, it adds it all up, and there's your price right there. So if you can eliminate a node, you save $1,000. But as I'm going to show you a little bit later on, sometimes adding a node actually allows you to save money. Sometimes adding more material allows you to save money too. Let's take a look at how that works. So over here on our member list, we can take a look and let's just adjust some of our tensile forces right over here. And you see I just searched that right now, or sorted that. And you can click on your compression force or your tension force to take a look right in here. But when I did the sort by tension and then the sort by compression, now you can see I've got all of my members that are 0 in compression right here. So here I'm looking at purely tensile members and holding down my shift key, I can come down here and I can highlight all of these members that are purely in tension. Okay, now you'll also notice that our tensile force relative to their overall strength for a 140 millimeter beam, 140 millimeter member, I should say, is the highest that we go up to is 0.38 of its strength. So as you recall from first semester, we talked about the strength being related to the cross-sectional area. You double the cross-sectional area of a tensile member, it's twice as strong. So we could bring the cross-sectional area of these members down to 1/3 of what they are. Now keep in mind this is 140 by 140, it's a square. Okay, so we can't bring it down to like 50 or 40, something like that. We've got to keep in mind that we're looking for a square. If we want 1/3, you can take the square root of 1/3 and figure out where we're going to. But what you can actually do in here is, I didn't want to pick up a different iteration. What I was looking for is somewhere right up in here. There is a tool right here we go that allows me to shrink the size of the members selected. So I've selected all these blue members right here. They're all too strong. And so I'm going to start dropping that price, and I'm going to bring it down at 110 by 110, and you'll see I've dropped the price of the bridge by $30,000 already. And now I'll run my load test animation. Now you'll notice they turned a darker blue than the last time I ran the animation, but they all stayed up. So that's good. When I come back now to my load test over here, you'll see that these factors that all used to be quite low, our highest was 0.3, they've now increased, and my highest is 0.5 right there. Oh, 0.6 right in here. So I'm going to bring that down a little bit more. I can make those slimmer still. I'm only going to click twice this time. Price of the bridge is now down to 228,000. Oh, very dark blue right on there. Okay, so that is probably as close as I can get on my first iteration. You can see that now some of those members are up to 0.9. Now, if I take a look at how the price is being calculated in here, you'll see that my product cost, I'm now ordering a second product in. So bringing that additional product in has cost me $1,000. But because I'm using a lot less steel, now my cost has gone down. Okay, because I'm just paying for less steel, even though I'm bringing in more products. So you got to keep your eye on your spreadsheet right here, both for the strength and for your cost as you're putting this together, and balance out the two. The other benefit that's happened by shrinking those members down is that they've become lighter now. Keeping in mind that a large part of what the bridge needs to support is the dead load of the bridge. By using less steel in the bridge weighs less, so the bridge can be less strong because it doesn't have to hold as much of itself up. That kind of makes sense, right? Lighter bridge doesn't need to be as strong because it's that light. The weight of the truck going across there is not insignificant, but relative to the weight dead load of the bridge, it's not that big. As you get to bigger and bigger bridges, the weight of the traffic on it really does start to approach insignificance. And in fact, what you'll find on truly large bridges is that the design factors for live load are far more significant for seismic load, designing for earthquakes, and wind load, designing for the wind blowing across it. We'll talk more about that in the famous Galloping Gertie to Coma Narrows Bridge a little bit later on. But the wind load on a bridge is probably one of the major live loads, more important than the vehicles actually. For a mid-sized bridge like we're talking about in here, certainly if you're planning to have heavy vehicles go across it, the live load does matter quite a bit. Okay, so here we go. We've got our tensile forces right in here. Let's take a look at our compressive members now. So you can go through and you can see that there's some members right in here that we can probably, actually I'll just tidy these ones up a bit more. And these last three, see now if I shrink them, just watch my price there. I'm at 228, basically 229 right now. If I shrink them down one, okay, there were enough of them and I made enough shrink that I actually reduced my budget, even though I had to pay for another size member coming in right here. So you want to optimize your number of members. Had I, and let me just go back one here, had I only reduced one of them, okay, I'm 228,900 again. If I reduce one of them, you see my price went up because even though I'm bringing in less steel, I'm now bringing in one of the 80 by 80s. So that is not worth doing to only bring in one of them. What I'm better to do is to bring that back up to be the same size as everything else, even though it's fairly lightly loaded. So I'll drop that down and let's just run one more test. And So there we go. I've knocked about 50 grand off the price from where we started. Now let's come back in here and let's take a look at the compressive members, because tensile members are fairly simple because it doesn't matter how long they are, the strength stays the same. But let's do a sort by our compressive strengths in right here. And well, here we go. These members on the end tend to be our highest strength compression members because they get quite a bit of load. When you think about the forces that's coming in here, pick this node right here, okay? Now, there's the weight of the bridge resting on it, but there's also the truck coming across it. So picture the combined loads of the truck and the bridge pushing down on this member right here. Now, what keeps that member from falling downwards? Well, it's got to be held up somewhere, and because these two members right here, number 6 and number 10, are horizontal members, if you push down like that, they'll just collapse downwards like that. They're not supporting it vertically. The only two members that can support it vertically are member number 5 right here and member number 21 right over here. This one, if it applies a vertical force on here to pull that up, is also going to apply a horizontal force pulling it over this way. Now, if this member number 5 is lifting this upwards, then this node right here is using member 5 to also pull down on this node right here. Okay, so if this node is being pulled down by 5, it must be being pushed up by 7. Now 7 right here, if this is pushing downwards onto 7, okay, that means this one's pushing downwards onto here. That is going to have a vertical component and a horizontal component. So we've been talking about component vectors in some of our other lectures. Well, that's why, is because when you picture this vertical force applied right here, okay, this is now pushing down this way with a vertical component pushing down on this node and a horizontal component pushing horizontally on this node. And of course, if it's pushing downwards here and backwards, this node must be pushing upwards and over right on the top. And then this one's pulling down right here. And then this one would rotate downwards if it could, but it can't, because if it wanted to spin downwards right here, it would have to move in that direction. And all of these ones, the force coming up right through here is pushing right against there, keeping that from rotating downwards. So our end members right here tend to get the highest compressive loading. And that's what you see right on here. In fact, those two end members, number 19 and number 1, are loaded up to 88 or 83% of their overall loading. Now, let's take a look right in here because we're using carbon steel bars. Come and take a look at the member details. Click on the member details tab, and here you can see the strength properties of the individual member. Okay, so what we've got in here is our length versus strength graph. And this is for tension, okay? So right here, we've got a tensile member, and that stays the same. If you think about a string or something, and I'll just grab a USB cable that I've got sitting right here. If I pull on that, okay, as we did with our tensile tests in first semester, it doesn't matter if it's this long or this long or this long, okay? When I pull on it, it's got the same strength. Yeah, might stretch a bit further because it's longer and elastic modulus is related to its length. But when you pull on something like that, it doesn't flex or buckle. But of course, we all know, the two rules of physics, F equals ma, and you can't push a rope. When I try to put a compressive force into something, it buckles or bends or flops or flips. And what controls how easily it buckles, bends, flops, or flips is the material that I've chosen, the length of the member, and the cross-sectional design of the member right here. So for this simple carbon steel solid bar, what you can see is that its compressive strength reaches a peak almost equal to its tensile strength when you've got a very short member. But as the member gets longer and longer and longer, it gets weaker and weaker until it's almost useless out here if you had a really long member. So some people have designed bridges that have these really long members in them, and they have to make them really, really huge, which drives up their price. Which actually, considering I want you to get cheaper each time you hand in the bridges, starting with a really expensive bridge probably isn't the worst possible place to be. But if you want to get into the top 5 or the top 10 and really pick up those marks, then you don't want members that are sitting out here. Here you can see the line running up and down representing the current length of our member at 5 point something meters. Okay, so what we could do is right now this is standing up just fine, but if we want to reduce the amount of steel that we're using in our bridge to help bring the cost down, we can change our cross section for our compressive members. And I'm just going to take all of my compressive members right here, and I got them all sorted up here by clicking on the compressive force to strength button. And let me just highlight all that. So there's all my compressive members, and I am going to turn them into hollow tubes. Okay, and you'll notice that my dimensions right here changed because now I've got 140 by 140 by 7, meaning that they've got an outside measurement of 140 by 140 and a wall thickness of 7 millimeters. And if I check at my member details right here, there's your diagram right there of what the hollow tube looks like. Now, Steve's kept this simple. He's only given you hollow or solid members. In reality, you get to choose from I-beams and a whole bunch of different designs depending on what you're doing. Okay, but it's enough choice that you get to talk about cross-section and the importance of it without getting too excited. Now, because we've lost all this material in the middle, we have lost some strength in that member. Now, we've lost a ton of weight, so that's a good thing, but we've also lost some strength, so it may not be quite as strong. So if I turn this back, you can see right now at our current length, if it's a hollow tube, we've got a strength of 475 kilonewtons, okay, that it can resist before it buckles. And if I change that back to a solid bar, we were at 1500 kilonewtons, okay? So making it hollow, if you keep the outside dimensions the same, obviously makes it weaker. There's less material. So if you're going to hollow something out, you also need to make it a little bit bigger, but you'll notice that the unit cost right here is $661 per meter. And if you go to a hollow tube, it drops to $184 per meter. So we can make this a lot bigger. And let's just come in here and increase that size. There, our strength is up to 550. Let's bring it up again a little bit. There we're up to 800. We might need to increase it one more time. And now we're up to about 1,000, which isn't quite as strong as it was before. But I think it's going to make our bridge a lot less expensive if it holds up right here. We can always, well, let's give it one more click just to make sure it holds up. We can always shrink them down later on. And there we're up around 1,100. And you can see the curve has changed a little bit. Instead of going and shrinking down really low, now it's actually a bit more of a straight line right in here, and we're getting closer to the strong end of it because of our cross section is providing more resistance to bending and buckling in that member. Let's take a look and see if it works. Ooh, maybe not right in there. Oops. So let's see. We come in here and now we've got some failed members, and you can tell that they failed, and you can tell they failed in compression because they're marked in red right here. Our blue members right in here, you can see are being pretty heavily loaded in compression. Here's our member list right here, and we had these 4 fail in compression, but it was really, really close. These ones down here seem to be doing just fine, so maybe I'm just going to take those 4 right up there, hold down the shift key, and I can pick those 4 members up. Okay, and just watch my price right there. It's going to go up a bit. but I'm going to make them a little bit bigger. Now I'm at 200,000. You'll recall on a previous iteration, I was at like 230,000. And so the last time my bridge stood up, I was at 230,000. Now by putting the hollow members in, I'm down to 200,000. And let's go ahead and run this right here. That's looking a little bit better. And we make it across. So now my bridge is $70,000 cheaper than it was when I started out. And just looking at these members right in here, um, you know, we're doing okay in there. Now, you can go on and you can keep tweaking the members, but the other thing you'll probably start to notice is that, well, let's go to member details, if the strength is such a big function of length, maybe for some of these longer members, it would be nice to make them a bit shorter. So you can come in right here and you can grab a node right here and you can tweak that node and bring it down a little bit and get it into more of an arch shape coming along right here. Now what we've done is we've shortened this node, but we've lengthened this node in the process. So maybe we want to move that one over a little bit. Now, when you're doing that, under your, where are we right in here? Under your view function right in here, you've got coarse grid, medium grid, and fine grid. And you start out on the coarse grid, but if you want to change that for fine adjusting things, just click on the fine grid, and you can come in here and you can move that just a little bit over that way. So by distributing that around, you see I'm under $200,000 now because instead of coming out here, I've kind of cut this corner and I'm using a little bit less material. Let's see if that's still going to be strong enough. Ooh, that doesn't look good in the middle. Ooh, made it. Okay, so by tweaking the locations of those nodes, you can start to reduce the mass of your bridge, and as a result, you can reduce the price of your bridge. The other thing you can do for some of these members in right here is you can come in and delete that member. There we go. And add a new node right in here and put a new member right in here. Now, if you just do that, okay, you've shortened that node right in here. That's fine, but if you run this, the bridge isn't going to stand up because you'll notice we no longer have a triangle here. We've got 4 nodes around this hollow space. What that means is that when we try to compress right down here, this force coming along the top presses down right here. This node's going to want to pop out to the side right here. So we have to add another member right in there, putting that back together. That one increased the cost of my bridge, but maybe if I come back and edit it down and do that to both ends, I can reduce that cost a little bit later on. You can see now these two members, right? Well, those two members right in there were nowhere near their failure strength because they were very short members, whereas this member up here now had to support that entire burden and it popped out. So you've got all of these little things to play with as you go along. And those are my first few hints on things to do for reducing the cost of your bridge. Use the sort tools on your member list to take a look at which ones are most likely to fail. Okay. Alternatively, use the sort list to find out which ones have no compression. Okay, because you can make those ones as thin as you want, so long as they're thin, strong enough, have enough cross-sectional material to support the tensile load that's being applied to them. Tensile loads are fairly easy to support because nothing will buckle. So you can play with that and you can play with your cross sections. Take a look at your member details and take a look at what type of member that you're using in here. Are you using a hollow member? Are you using a solid member? If it's in compression, chances are it's going to be less expensive to use the hollow member because hollow members are optimized for dealing with compression. You can also get in there, and when you're working on this, you'll see that there's a choice of 3 different steels. And you'll recall from first semester, we talked about plain carbon steel. We talked about high strength, low alloy steel, and even quenched and tempered steel. All of these are options that you've got available when you're ordering them. What you'll notice, however, is that while carbon steel is our weakest, it's also our cheapest. The advantage of going to a stronger steel is that you need less of it. And as you get less material on the bridge, your dead weight of the bridge goes down. Because the dead weight of the bridge goes down, now your structure no longer needs to support quite as much mass. So sometimes going to the more expensive steel is really good if it lets you lighten the bridge and therefore have an overall lighter structure because you don't need to support as much dead load. But it costs more to get the fancy material, which is why you need to keep track of your prices using this little down arrow right here to look at each iteration and say, okay, where was the check mark where I stood up and had the best price in here, and where were the ones that failed? Don't want to do the ones that failed, and then take a look in here and figure out where were you going in when you were working in the right direction. Now, the other thing I'll do while I'm running this software is I will do a save as, okay? And every 15 to 20 minutes, I try to get in the habit of doing save as and saving the file, and I might put a V5 next to it, or what I'll usually do is I'll put the price of the bridge into the file name of the bridge. So I'll say, this is Jason Bridge, Jason Thursday, 202,000, or just Jason Thursday 202, so that when I come back to look for it and I want to find, which was the cheap bridge, then I'll find it. The other thing that happens is in the unlikely event of a computer crash or power outage, while you're in the middle of a save, if you keep changing the file name, you always have your previous version of the file to go back to. Okay, so just good computer habits for any software that you're using. Save every 15 or 20 minutes with a new file name, and that way you will never, ever lose more than 15 or 20 minutes worth of work. Alrighty. You guys have slightly different bridge configuration. You've got one more node in there to deal with. I went with the easy one here, but as you can see, it didn't take long to knock $70,000 off the price of the bridge. Some of you guys have already gone through and done the easy things, so you might want to start experimenting with setting your grid to the fine grid so you can move things about a little bit on here. You might find that moving things to just a little bit more of an arch shape helps. Even though that's going to make your bridge slightly more expensive, it might redistribute the stresses differently so that you can come back and make things a little bit lighter. You might find that using lighter weight materials, higher strength materials allows you to put less steel into your bridge, allowing you to use slimmer members, making the dead load lighter. Lots of options in here. The help file is excellent, and there are other tutorials online that also describe the similar concepts for West Point Bridge Designer in different ways. Have at it. I'm looking forward to see what you've got for our next upload period, and enjoy. I've spent a lot of hours on this piece of software, and I've got to admit, it's really hard for me to stay ahead of some of my grade 9 and 10 students. The ones who get into this, go home, download the software, and they just keep beating away at it for hours. They do that instead of playing video games or whatever they're into, because it's a lot of fun because you can go head to head with your friends doing something other than a first person shooter. And they kids by and large tend to like the software, and it gives you an entry point to get people starting to think about how does stress flow through a structure. I really like this design right, or this design, this animation right here. and the fact that it comes back and it shows you how those forces flow through the various members. And when you're on that load test, you can see the loading coming in there and you can figure out, okay, well, if that one's pushing up on that node, then that node's pushing over there and that node is coming down this way. You can start thinking about all that so that when we come to doing the math behind it in class, you're not trying to figure out, well, what's he talking about? You've actually seen it in action in a friendly user interface, because we do have some math coming for you, but not today. All right, where's the off button? I should just press off. I think I can go have some lunch now.